Hi, my name is Ayman Fahad. I will explain about the technical report for all structure analysis. Introduction. The technical report is prepared of the part of requirements for the advanced structure analysis. This building consists of conventional reinforced concrete frame system with 200 mm thick shear wall for the left core. The frame system includes reinforced columns, beams, and slabs as the main structural system to support the building. Furthermore, the perimeter beams are assumed to support full height brick walls all around the following section. We'll highlight the relevant code of the practice and the material used. Material data. We have concrete grade 30 with the 20 mm aggregate for column, wall, beam, and slabs. For the loading condition, we have dead load for reinforcement concrete density 24 kN per meter cube. Then we have 115 thick brick wall, which have normally 2.6 kN per meter square. Finishes, which have 1.0 kN per meter square. Then we have the imposed loads for computer room 3.5, lobby for washroom 2.0, and office we have 4 kN per meter square. For the sizes of structural elements, we have beams 250 by 600, and the slabs, all of them are 150 millimeters. All the column sizes have 300 by 300 millimeter, and the shear wall thickness have 200 millimeter. So the tool used for the structural analysis, we use StatPro was used as the mean for the structural analysis. In this particular project, it was used to model the typical floor as structural frame with shear wall. The first one was modeled to support uniformly distributed area load, whereby the second and the third ones were modeled to support uniformly distributed load with point load and line load at the midspan respectively. Based on the output extracted from the StatPro software, this section will explain the structural analysis of the typical upper structural element in terms of yield, line pattern of slabs, collapse moment, elastic moment, and maximum forces of the frame and the deflection of the slabs. The discussion will include some figure for the purpose of elaboration. The purpose of using yield line method is to determine the ultimate bending moment at the collapse state. It is an upper bound limit in which the protected failure load of slab for a given moment of resistance or capacity may be higher than the true value. The short edge of the one-way slab contributes in supporting the load intensity from the slab, forming part of the yield line pattern of the entire slab. For two-way slab, all the four edges take part in supporting the whole slab, whereby the irregular slab has special yield line pattern as it has multi-edges. The calculation of this collapse moment was carried out based on StatPro outputs. It summarized the negative and positive collapse moment of short and long span respectively. For the slab 2, as it's subjected to uniformly distributed area load and point load at the midspan, and slab 3 that has irregular shape whereby the collapse moment and stresses distribution is totally different from those one-way and two-way slabs. Slab 4 is one-way slab supporting uniformly distributed area load. The last slab panel is subjected to uniformly distributed area load line load due to the self-weight of the brick wall. Next is elastic moment. The maximum elastic moment was found to be the first interior support, as the slab is supporting purely area distributed load. The maximum elastic moment was found to be at the midspan in both directions, as the slab 2 is subjected to uniformly distributed area and point load at the midspan. The distribution of the moment varies as slab 3 has irregular shape. The higher concentration of the moment and stress, as explained earlier, are found to all around the edges, as it is the critical area of stress transition and distribution. and distribution. For slab 4, the maximum elastic moment is occur at the support as there will be higher interaction between the slabs and the shear wall due to the high stiffness of the shear wall. The last slab panel is subjected to uniform distributed area, load, and line due to the self-weight of the brick. Therefore, the concentration of the moment and stress are found to be at the mid-span. These are the frames labelings, frame for the bending moment of the frames, bending moment and shear force diagrams for the forces. So the section will show in this section it will show the bending moment and shear force and axial forces in force of columns in forms of support reaction. The bending moment and shear force of each frame will be discussed separately. Furthermore, the support reaction of the entire frame will be also discussed. The maximum support reaction occurred in the internal column of frame 2 as the column support at the main frame as well as the secondary frame. On the third frame, beams are not subjected to any impact point load. The distribution of shear forces and bending moment has no significant impact in terms of variations. And frame 4 is considered as perimeter frame and subject to lower load intensity compared to the other internal frame. Therefore, the bending moment and shear forces of the said frame considered to be the lower among all frames. So as frame 5. So next is the support reaction of the entire frames as shown in the figure 31. The maximum support reactions occurred in the internal columns and in frame 2 as the columns support the frame as well as the secondary beam. Next is slab deflection. Normally the short span controls the deflection of the slab and varies based on the end condition of the support, whether restrained or not. Based on the end condition, the calculation of the allowable deflection can be calculated and compared with the actual slab deflection. The deflection of the slabs will be discussed in this section. As mentioned previously, the second slab is subjected to the point load at the midspan. Therefore, the deflection at the midspan is critical. However, as the size of the panel is considered not huge, the effect of the point is not extremely critical. On the other side, the deflection of the slab to is shown in figure 33. In this figure, the slab has different deflection behavior based on the yield line pattern. It varies all around the panel as shown in the figure. The maximum deflection follows the yield line pattern, forming 3 different types. As the last panel shown in figure 36, support uniformly distributed area and additional line load at the midspan. There are 2 different values for the deflection. The first value is at the midspan underneath the line load, and the second value is at the midspan along the panel in between the supports. So, in conclusion, to sum up, this typical upper floor of the office building has 3 types of slabs: one-way, two-way, and irregular slab. Based on the structure analysis performed using StatPro software, those 3 types of slab exhibit different structural behavior in terms of stress distribution, elastic moment, and deflection as well. On the other hand, they also subject to different type of load pattern, such as pure uniformly distributed area load, point load, and line load. On the other hand, the frame also have 3 types, for example, single span, 2 span, and 3 span frames. In structural wise, they also subject to different type of loading. Thank you.